afternoon, everybody. I will not speak about Himalaya hydrology, but I hope that this is an interesting topic. What I'm talking about, high impact, low probability events. Some say black swans or unprecedented events or worst case events. And I would like to discuss those events, why we ignore them very often, and why we are surprised, and then a bit about the processes and management. Okay, I will give one example, but there are countless examples around. So one example which was very important for us in Europe, and particularly in Germany. In July 21, there was a large flood with almost 200 people dying in Germany. And if somebody would have asked me prior to July 21, you're working now for more than 20 years in flood risk, so flood fatalities, is it a problem in Germany? I would have said no, that's not a real problem. So not only the people that were affected, but also people who are supposed to be experts and have worked for a long time were really surprised by this flood. So to the left, you see the R catchment. This is the flood time series, so annual maximum peaks. And you see that we have systematic measurements by the water administration. We had them for 50 years. For 70 years, 74 years. And then we had this unprecedented flood. So this was a real surprise. This is, again, a part of the R Valley. So in Europe, a couple of years ago, the European Flood Directive was introduced, and all the member states are obliged to provide flood maps. 3 scenarios: the 10-year flood, the 100-year flood, and then a so-called extreme flood. And it's open to the local or regional administration what this means. And this shows the inundation areas of the extreme flood. You see here a few very minor inundation areas in this scenario, right? But if you now look at the event, and this is a simulation that we did in the week directly after the event. So this road, this yellow road is cumbersome. This is the road here, and you see that we had inundation covering a large part, and the official flood map showing the extreme event had no clue. Yeah, so people were really surprised. So this is just one example, and there are countless other examples that quite often, at least at the global scale, we are surprised by this kind of black swans nobody had thought about. So this is one point. The other point, and this is one slide, I have this, that due to climate change, but also changes in our society, land use changes, global supply change, and things like that, risk is increasing. And this, maybe you have seen this paper. This group has looked at daily rainfall or precipitation extremes all over the globe, so analyzing several thousand rainfall stations, and looking at the records. It's difficult to do a statistic with records, but if you have a very large sample, then you can do that. So they were looking at records. So a record is a observation that has not been measured at that station before. Yeah, in the observational window. Okay, and the horizontal line and the blue area shows the number of records that you would expect in a stationary world, right? Also, if the climate would be stationary, the system would not change. Once in a while, you would expect a record. And this is now the count of the records that we have observed, normalized and as anomaly. And you see that over the last 20 years, on the global level averaged, we had more than 25–30% more daily rainfall records. Okay, and you see, well, India and Germany are among the high-ranking regions here. Okay, so we have these records, so we should prepare ourselves for this kind of black swans. These are the four topics that I would like to cover very briefly, all of them. The first one is, so why are we so often surprised? Why are we not well prepared for this kind of events? And I think there are several reasons, and one reason is a kind of economic reason. At least in Europe, we base risk management quite often on economic considerations, like cost-benefit analysis. And then we have this idea that risk is the probability of a certain damage occurring. We use the expected annual economic damage as measure for risk, and which is sensible because it minimizes the long-term average damage. But the point is that these extreme scenarios, the events with a very low probability, they have a small contribution to the expected annual damage. Well, of course, it depends on the local situation, but we have looked at that for whole of Germany, and this is just one catchment. And here you see the expected annual damage. The circle shows euros per year, and then you see these colors, and these are the contributions of the different events. And you see that the largest contribution comes from the frequently occurring floods. And the extreme floods, like the 1,000-year, the 10,000-year flood, they don't have a large contribution. So if you do cost-benefit analysis, then it somehow says, well, take care about the smaller floods, the more frequent floods, and the real extremes are not that important. So it assumes a risk-neutral perception, but we all know that this is not true. 1,000 incidents with one person dying is not the same as one incident with 1,000 people dying. So for society, this can be very different. So typically, we ignore those indirect and intangible consequences that are very important for these extreme events. The second reason, or another reason which I think is important, are psychological reasons. I took this nice graphic from the internet. This is a collection of cognitive biases. So we all have our mental models. We have an idea how the world functions. For example, there is confirmation bias. We have an opinion, we have a concept, and then we tend to look for information that confirms our mental model, for example. There is single action bias. When there is a problem and we take a single action, then we tend to relax because we have acted. But this single action may not have changed a lot the problem, right? So there are some unconscious biases. And there is an availability bias. I think that's meanwhile very famous. We have a hard time to estimate probabilities, or in another way, the probability estimates that we give are closely related to the availability of the information. If we have seen an event like that in real life or on social media or whatever, if we can relate to that, then we attach a higher probability and vice versa. Then there are some nice studies like people perceive desirable events as more likely for themselves as for others, which is why? But we all buy tickets for the lottery, although the chances are super slim, and we think we will not be affected by a flood. Okay, people cannot predict negative effects of severe flooding when they have not experienced it, and so forth. So I think that's these kind of psychological issues are really important. Okay, now, and this is also then difficult to communicate this kind of events, because when I talk to a layperson and say, well, imagine there could be the 10,000-year flood and it would be disastrous for you, then this is difficult to understand. So, well, 10,000 years, why care about that? So we need also to find ways to overcome these biases and to communicate these real extremes. Some slides on processes. So what we often do is we extrapolate from what we observe to the extreme range. And this works well in case we can extrapolate. Yeah, we have more or less the same processes. Coming back to the R-flat, this is the time series you have seen. If we do typical flat frequency analysis, you fit a GV to this large sample, 70 years. It's a large sample in flat frequency analysis. And then you plot flat peak of 21. You read a probability, a return period of 200 million years, which is clearly bizarre. This cannot be. Yeah. Okay, you can do other things. There have been historical floods in this valley. Here, a photo of 1910. This is a mass grave because of the flood fatalities. And if you now include those 5 floods that have been reconstructed, and interestingly, the one 200 years ago was estimated to be kind of exactly the same peak that we have seen in 21, then you get a return period of around 8,000 years, which is much more plausible. But still, this GEV statistical model somehow does not seem to capture these large floods, right? Maybe there is something going on. Now, if you plot the same data along the day of the year where these floods occur, the blue points are the annual peaks of the systematic measurements. The red points are the 5 historical floods. Then you observe something interesting, that most of the floods occur in winter, but the winter floods are rarely beyond 200 cubic meters per second. Summer floods are rare, but they can be tremendous. So maybe we have different processes, right, in the atmosphere, but also on the land surface. And we looked at that a bit more closely, and you see that also the response of the catchment has been very different, very fast, very high peak in relation to the flood volume comparing to the typical winter floods. And now the hypothesis is that these extreme events are different from the typical events, yeah? And these differences can occur in the atmosphere, in the land surface catchment, and also in the river system. And I think, meanwhile, there are quite a number of studies that have looked at the storm tracks or the atmospheric situations that cause normal floods and extreme floods. And in many cases, we see, well, there tend to be a difference in the storm tracks, for example, on the large-scale atmospheric processes. This is an example from the Ohio River, where the 10 largest floods in the observational window have been linked to a certain atmospheric moisture transport pattern. This is an example for catchment processes provided by TU Vienna. So they mapped a small catchment in the Alps in Austria, looked at the subsurface storage and runoff generation, and then they developed a model which was specifically tuned to this situation. And this is now the simulation result. This the horizontal axis shows the contributing area with fast surface runoff. And you see an interesting behavior. Up to 150 millimeters of event rainfall, 10% is contributing. And then there is a kind of threshold, and then it kind of explodes. And interestingly, this is then also seen in the flat frequency curve, where we all the observations are aligned more or less with the same scale or along the same line slope, and then there is this step change. And the third example is a quite old paper that we did many years ago, where we looked at the river system. And here we do again a flat frequency analysis, and we have 3 models. Green and blue is the statistical model, so fitting a distribution function to the observations. And red is a simulation model, a probabilistic simulation model that takes into account the processes. And you see in the extreme range, there is a different behavior. And this is a very trivial example, but still it's often not taken into account when we do return period estimation. Here, dikes are overtopped or breach, and then a lot of water is flowing into the dike hinterland, which reduces the peak downstream, and that's why we have this kind of upward bending in the flood frequency curve, which is a good thing for our neighbors in the Netherlands, because first the dikes in Germany at the Rhine will be overtopped and will reduce the flood peaks for our neighbors in the Netherlands. Okay, so that's, and the message here is, yeah, don't just simply extrapolate, try to understand the processes and try to understand whether we have the same processes when we look at the frequent floods and the rare floods. Okay, now I'm convinced that we, beyond estimating design values and so forth, what is asked for building flood defenses and so forth, we also need to think and develop this kind of worst case floods or black swan floods or however you call them. And now we have an issue, as I already mentioned, an issue with communicating them and developing this kind of plausible floods. I will show now two approaches that we have used. Stochastic simulation. So here is the idea that we have a process model. We embed this process model in a stochastic environment, and we generate then not hundreds, but 10,000s of events, a huge event set. And then we try to find the patterns and extreme events. Another approach that I would like to show are so-called downward counterfactuals. So a counterfactual is you think about the past and you say, well, it could have developed in another way, as in reality. And often we think about positive or upward counterfactuals. We think, well, if I would have left the house 2 minutes later, then I would not have had this accident, yeah? But here we can specifically look for downward counterfactuals. So we take an event in the past and say, well, can we twist it? And let's see what happens and twist it in a negative way. Okay, and again, the idea is that we will learn something about these kind of extreme events, and we can communicate them better because here one example, this is not provided by us, but by another group. We had a very strong winter storm with a lot of damages in southwest Germany, and all the black bars shows the damages at the municipality level. And now the colleague said, what if this storm would have occurred with 10% higher wind gusts? And then you would say, well, then I increased the damages by 10%. But the result was really striking because there was a strong nonlinearity in this model. Yeah, so we can maybe detect this kind of responses. Okay, the example now on the stochastic simulation. So we have developed over the last 10 years a stochastic weather generator, generating synthetic weather for Germany. And to the left, you see a big disaster in Germany in 2002. So you see daily rainfall patterns. And to the right, you see a synthetic flood generated by our software. Yeah, and the idea is that you cannot distinguish between the real events and the synthetic events, and that the statistical properties are the same. And then we run this for 10,000 years, and we transform rainfall via hydrological model, a flood inundation model, or a flood routing model, flood inundation model, and a flood impact model in 10,000 years of spatially distributed flood peaks, inundation areas, damages. And then we do statistics. And the hope is that we can have extreme situations, unfortunate superposition of, let's say, antecedent conditions in an area where floods are generated. Yeah. Or we have dike overtopping in an area we have large acids. And now I will come back in a minute to this tool, but now I will show two past flood disasters, and then I will compare the output of our tool to those past disasters. I selected a winter flood and a summer flood. This shows the winter flood of 93. And now you will see several of these maps of Germany with those circles. Each circle is a stream flow gauge, and the color of the circle codes the return period for this event. Yeah, and you see red is bad, okay? And then this is the same information, but just shown as histogram of the return periods. So this was the real event, and maybe you try a bit to remember. So it was a quite widespread event covering a large part of Germany, and then quite many red catchments. This was the summer flood that I mentioned earlier. It was just at the border to Belgium and the Netherlands. Quite red here, but a smaller area. Now, some synthetic floods. Now we have 10,000 years of floods, and this is now year 25. And you see, this is quite similar to what we have seen in real life in winter 93, a bit more severe. This is quite similar to what we have seen 3 years ago, a bit more severe and a bit shifted to the northeast. And this is an interesting one. This would be a real disaster. So you see that large parts of Germany are covered with dark blue or red. And if you now look at the timing, then you see that our weather generator in the system generates in January a flood in in central and west Germany. These are the triangles. And then in March, so 2 months later, we have a huge flood, very high return periods in the south, in the Danube. And we did this example, this calculation 2 years ago. And what I found interesting, the Germans know, of course, this year we had in January a flood covering here Lower Saxony, and then in June, not in March, a flood covering the Danube, and it was not that severe. But it's interesting to see that our weather generator provides those kind of scenarios. Okay, and what we see from that, so it can be much, much worse. Then that means 5 or 10? 5, okay, I'm quick. So the second one is now the counterfactual approach. So we are looking for, we're taking past events and looking, can they get worse? And there are many approaches how you could do that. A very simple one is spatial counterfactuals. You say, well, there was this storm track coming from the Mediterranean area and then going through East Germany and then bending and then coming to West Germany. And it could have occurred 20, 50, 100 kilometers more west or east, whatever. And so we just shift the event rainfall in space. And by that, we generated 3 distances and 8 directions, so 24 new floods. And then you see how the picture changes. So again, this is now the winter flood as observed. This is a shift southwest 50 kilometers, so a little bit less severe. This is the shift 50 kilometers northeast. Similar picture here. Summer flood 21 as observed. Southeast 50 kilometer, more or less the same. But again, northeast 50 kilometer, it would have been much more severe. And now you can go to people and say, yeah, okay, maybe you think your risk management was very good, but maybe this was sheer luck, yeah? Because the storm could have hit you more directly. Okay, And then one slide about risk management. This is a graph where we have the probability versus the damage, and we have a large spectrum of possibilities for fighting against extreme events. But they tend to have a certain domain where they are more useful, right? And I think we need to spend more thinking in this domain and think about this kind of really extreme events and how we can respond in case they occur. Yeah. And I want to show just one recent example from our work. In Germany, we have a very well working flood forecasting system, but the forecast stops at river gauges. It provides water levels within the next 24 hours. So it says maybe you will have 5 meters 50 at this gauge. And now imagine you are responsible for a hospital 10 kilometers downstream. So what do you do? Is this a problem or not? And now the models are so fast and there is so much data available, like digital elevation data, OpenStreetMap, that you can run inundation simulations and estimate the impact on the fly. And this is, again, the R Valley. This is our model. The simulation takes 7 minutes, and the lead time, so the forecast at the gauge is 24 hours. Of course, with large uncertainties, yeah. But I think that's a way to go, to provide richer information for disaster managers and affected people. And then you can transfer the velocities and water depths, for example, in an indicator which shows the risk of drowning. So all the purple areas show regions where you can't stand due to high velocity or large water depth. And you see that for this event, large areas within the inundation areas would have been dangerous. Okay, that I wanted to share. So I think we need to spend, at least in Europe, I have no idea how you do that in India, but I think we need to spend more thinking on this kind of black swans, look at the processes, and then also think more about managing them in case they turn up. Thanks.